Okay, so I have solved all four problems. So let's quickly go through them. Yeah. So first problem is count monobit integers. So we are given an integer n, and it is said that a number is called monobit if all bits in its binary representation are the same. So like we cannot have 101. This is not allowed. So return the count of monobit integers. So the idea for this is this also includes 0. So except 0, or we cannot have a number like 000. That's not possible. So we will only have 0, 1, 1, 1, 1, 1, 1, and all these numbers are in base 2 in binary. So this is a simulation problem. Like uh, we can do, we have a current number and we have the answer count. So while the current number is less than equal to n, I increase the count by 1, and the current number, basically if the number at this point is 111, so I will shift it one bit, so it will become 1110, and then I will OR it with 1, so it will become 1111. So this way all the bits in it will be 1. So this is the idea for problem 1. Problem 2. So this was an interesting one. So the idea is we are we are given we are given an array. We are given an array, and we can remove some subarray of it, just such that it is not the complete array. We are not allowed to remove the complete array, some subarray of it, and the remaining attaches. So at we start with Alice, and Alice wants to maximize the final element, and Bob wants to minimize it. So we want to see the final answer. So this is actually an interesting problem. So first my idea was, if the maximum is present here or here, if the first or the last element is the maximum, then we will just, let's say this is the maximum, so we can just remove this entire subarray, and this will be a maximum. So we can get this value since Alice is the one playing first. And similarly with the last one. Then one more observation is, since we cannot remove the entire array, in the worst case, at least this or this, either of them, the first or the last element, will survive. Others can be removed. So in case uh, the first or the last element is the minimum number of the array, if so, let's say is array 0, 1, 2, 3, 4, let's say. So if 0 is the end of the array and we don't remove it, we remove something like this, then Bob will definitely remove the this portion and just get 0. So we have to remove it. So, and after that also, like if there is, let's say, a big number in here, let's say there was 20 here, then also we cannot get it because Bob will definitely remove this. Bob will definitely try to remove this value, and that's why we cannot never get the middle element. So this is actually a very good intuition. I was not 100% sure that it would work. So the answer is just that it can be either the first element or the last element. So Alice has the choice, so it can uh, choose the maximum of them to survive. It can remove the minimum. So this is literally the answer. The first element in the array and the last element in the array, it's maximum. So this was an interesting problem. Coming to problem 3. Okay, yeah, so this is just an implementation problem. So we are given an Uber-like system. So we have a rider ID which wants a cab, let's say, and we have a driver ID who was available to take some riders. So we will match them. So it says to match the earliest available driver. So that's why I have used a queue here to I maintain the rider and driver IDs in the queue, and the earliest waiting rider and the earliest waiting driver are added accordingly. So and if none either of them is not available, then we cannot have a matching. So it is -1 -1. in this, and otherwise, let's say a rider cancels its ride, so we have to cancel it if the rider exists and has not been matched. So this is the condition actually which I, because of which I got a wrong answer here. So my initial idea was, like, I took these queues, rider and driver, and decided to have a set name cancelled. So whenever I'm cancelling a rider ID, I'm adding it in cancelled, and whenever I have to match with it. So whenever I'm matching it, I'll pop the elements from the queue. But before that, I will remove all those riders from the front of the queue that are cancelled, that have cancelled. So this was my idea, like remove them, then have the driver and rider here. But the issue with this one is, in this test case, let's say a cancel rider request had ID 1, but rider did not exist as it says. If the rider exists, so a rider did not exist, but my cancelled set had one already, and after that, when one was added, it was considered cancelled. So this is a bad case where my this is a case where my code failed. So besides this queue, I am also maintaining an in rider set. So this elements and these elements will be absolutely same. It's just that in B tree set the query is faster. There actually exists a data structure in Java known as linked hash set. Linked hash set. So this maintains the order and has a faster search time. So this is the ideal data structure for this problem. So provides O1 times add contains remove and maintains the order. So but I have made used it. I've made it using queue and inrider. So yeah, this is the idea for my problem. Like in case when I'm adding a rider, I'm adding it in rider as well, and when I'm removing it from here as well. And I will add it to cancelled only if the rider exists at that point. So this is the idea for problem C. Problem D. Okay, so we are given an array and we have to find an alternating array such that it first decreases, then increases, and so on. Or either it increases, then decreases, and so on. So, and we are allowed to remove at most one element. So the way I have solved it is, let's take this example only. So let's say the array is 2132. So better to visualize it this way, 2132. So in this the entire array is fine, but like how we'll do it is, I maintained four arrays, like so I maintained four arrays for increasing, decreasing, and from left or right. So these four combinations. So if let's say the I here is 0, 1, 2, 3, and I have maintained a prefix 0, or let's say the decreasing, prefix increasing, suffix increasing. So if at point I we are reaching point I from the left and we are decreasing the value, then we will increase it by 1. So this is 1, because going from 0 to 1 our value decreased by 1. Similarly, in case the value increases, we will add 1 here, and from 2 to 3 the value decreases again, so we'll add 1 here. Similarly, in case of suffix, we will go from right to left. So from 3 to 2, the value from 2, I mean from 2 to 3 the value decreases. So we can have this 1 here. From 1 to 2 the value increases, so we can have 1 here. From 0 to 1 the value decreases, so we can have 1 here. So now in this we will have this, and if you notice the other values can be put as 0. So now the observation is that if we have to choose an alternating subarray, then we have to check the elements in this fashion. So these three these three elements, they form a subarray. I mean, these three differences basically, these three comparisons form an alternating subarray. So three comparisons means four elements. So all these four elements are forming the subarray. So this is the idea. And similarly, from if we see from the suffix side as well, we get the same subarray. So this is the idea. You can check for prefix, if it increasing to AI, if we are increasing to AI, then 0 will have 1. Otherwise, the 1 will have 1. So this is the convention I have used. And then the prefix sum is taken this way only. For prefix 0 I am taking uh, 1 I minus 1. So like in this diagonal fashion. And same for the suffix. So now we have to find the answer. So initially the answer is, in case we don't remove any element, then what is the maximum we can take? So here actually we have taken a prefix sum of these values in a diagonal fashion. So here it is 0, 0, 0, 0. Here 0, 1, 2, 3. This is the prefix sum till this part. Similarly, here we have take the suffix sum 0, 0, 0, 0 and 0, 1, 2, 3 this way. And now to check the other condition, removing one element. So let's say we remove this index I, and now we have two cases. Like if this value is smaller, if the I minus 1th value is smaller than I plus 1, so we will have something like this here and something like this here. AI, let's say was something here doesn't matter. So this is increasing. So from I plus 1 we have to check a decreasing suffix, and here we have to check for I minus 1, we have to check a decreasing prefix, because this must have come this way. So this is the idea. Like uh let's say AI minus 1 is less than AI plus 1, then the from the left side, the the longest decreasing part we have till I minus 1, and on the right side the decreasing part we have from I plus 1, and plus 2 because we, as we see, we seeing the differences, so there's one more element in each of them. So the to maintain that count we done plus 2 here. So this is the idea for problem 4. So yeah, that's it from my side. Thanks for watching. Bye.